Hi, welcome. My name is Josh Turner. I'm a scientist here at the LCLS, as well as the Stanford Institute for Materials and Energy Sciences. And today I'm going to be talking a little bit with you about qRIXS. So this is a new instrument. I want to talk to you a little about the capabilities and where we are with building this new instrument. This is for the workshop here. In case you don't know where you are, SLAC Facilities Fundamentals Workshop. So I also like to say one quick thing. Full disclosure is that largely these slides are provided by Dr. Georgi Dakovsky. So he's been a main person developing this instrument. So these are mainly his slides. I tweaked them a little bit. So let's get started. So first of all, I think probably everyone knows this. We're at the LCLS. This is an overview of the LCLS instrument. I'm sure many people have seen a lot of talks on this so far. And this is one of the new instruments as part of LCLS 2. So this is a new facility which is being has been constructed and is being commissioned right now, which is delivering high repetition rate. Here's an overview of the facility. So here on the bottom, if you can see my cursor, I hope so, since this is on video, we have the 4 hard X-ray instruments as part of LCLS. And in the near hall, this is the far hall. In the near hall, we have a series of instruments as well. Previously, there used to be 2 instruments here called AMO and SXR, which are no longer. XPP is the one hard X-ray instrument, which is part of the near hall facility. And in replacement for these 2 soft X-ray instruments, we now have TMO and TXI, here shown in blue and pink. And then we have monochromatic soft X-ray instruments as part of the LCLS 2 facility. And these are shown here on the floor above. And they're split into 2 different instruments, the qRIXS and the qRIXS, which I'll be discussing a little bit further here. But first, let me just give you a quick overview of some of the work that's been done on the previous soft X-ray instruments with the low repetition rate. Well, low means 120 hertz. The first is an example of an ultra-fast chemistry experiment. This was a ruthenium substrate, which was prepared carbon monoxide molecules. And by pumping these systems and doing spectroscopy, both absorption as well as X-ray emission spectroscopy, one is able to study the electronic structure and how it changes. And there's been a lot of theory about this idea of a precursor state, you know, when energy is given to these molecules, but bonds are not formed, and how that changes in time. That was the first one. The second one is on a multiferroic. So this was an experiment where soft X-ray radiation at the manganese edge was used to study magnetic structure. And when the pump comes in at a resonance of this electromagnon, which is this excitation, which is a combination of magnetic and electric polarization coupling, and by pumping this with terahertz radiation directly with an electromagnetic field, we could see the motion of this and study the spin dynamics of the system using soft X-rays. And then lastly, this was one of the first RIXS experiments that was done in the soft X-ray range at LCLS. This is on a transition metal complex, which is really a benchmarking study to study how these molecules, how the charge is transferred and how the spin channels can change by studying these liquid chemistry systems and exciting them with X-rays. With optical measurements and studying the response with X-rays, studying the spectrum. Here's the papers here, so you can look at that as well. In addition, there's been a number of time-resolved RIXS examples as well. So the first one showing here is LBCO, where you can see the spectrum that's emitted from the high-temperature superconductor. And by looking at this peak here, you can see a dramatic change with time. And this serves as a way to, by looking at the spectrum, seeing which parts are changing as they're getting pumped with lasers. The second one is a copper germanium system. This is a spin chain, these one-dimensional systems which don't form long-range magnetic order. And by using RIXS, what the team was able to do was to study these short-range magnetic fluctuations. In this case, studying this exciton peak, this Zhang-Rice peak, which is shown here, and seeing, you know, again, by looking at the spectrum and seeing which parts of the spectrum change while they're being pumped, we can sort of unravel what's happening in this type of a system. The one down here is V203. This is a famous mod insulator material. And this was studying orbital excitations using RIXS, time resolved RIXS. This is one of the first, I believe, time resolved RIXS experiments in the soft X-ray range of LCLS. And here the idea was to, by pumping it, you can compare to different static spectrum using a synchrotron and sort of see these states that were similar. And the last example here is recently a publication by Wandel. This is done on YBCO, another high temperature superconductor. And this was slightly different. So this one was not doing RIXS, so resonant inelastic X-ray scattering, but it was doing elastic scattering. But in this situation, by pumping it and looking at the ultra-fast dynamics, one is able to resolve the different components of these fluctuations. So there's, for instance, there's different components which are not perturbed by the laser. So this is another way to go about studying the different excitations and how they behave in ultra-fast timescales. So let me just say a little bit about LCLS2. I think if you're in this workshop, you've probably heard of this already, but let me just give you overview for completeness. So the big change with LCLS and free electron lasers in general was compared to existing storage rings 1 billion times peak brightness. And this change in peak brightness allowed us, and it's continuing to allow us to do many different types of experiments. With LCLS2, there's a number of different capabilities which make it unique, but one of them is shown here on the right, which is the change in high average brightness. So compared to LCLS1, the peak brightness, the pulse energy per X-ray pulse is about the same. But because of the high repetition rate, as a factor of 10,000, the average brightness will go up by 4 orders of magnitude. So this is, just a quick overview, and also the repetition rate and the stability also will make these instruments that are running on the LCLS2 quite interesting, and not only to sort of do experiments we've been doing previously at much faster times because of this repetition rate increase, but in addition, there's new kinds of experiments that can't be done without facilities like this, which we'll discuss in a moment. Here's an outline of the instrument I'm going to be discussing. The main point here, I don't have to go into details, I guess, because this is a recording, so you can pause it. But the main thing here is that the beamline has a mirror which reflects the X-rays up into another floor. So this has an exoslit which is sitting on the roof in another hutch, and it comes into the upstairs RIXS hutch, which we are going to go view momentarily. I'm going to show you live the instrument, okay? So be prepared for that. So we don't have to look at this because we're going to go see it in real life, but the main idea here is just to give you an overview of the instrument. So the beam comes from the top down. Here is the qRIXS end station with a spectrometer that I'll be showing you. And then there's also a second instrument, which is called qRIXS, which I'll be discussing a little bit as well. Here's a picture inside the qRIXS station for anyone who hasn't seen this. I guess most people aren't going to see this because we're doing a virtual conference here, but if you come visit, you can come look. But this shows the where the system is, where there's a liquid jet system in the chamber, where the samples can be studied using these streams of different types of molecules, and look at the spectrum coming out. This picture on the right, I'm actually not sure what this is. So moving on. Here's the liquid jet delivery. So a big part of this is delivering different types of molecules in different states. So the method of choice is a thin liquid stream shown here. But there's also been a development where, mainly led by Jake Korlek, where we can now produce very thin sheets. So a very thin liquid stream, but is in a sheet. So a lot of different types of studies can occur with this as well. So this has been a recent development only in the last couple of years. Now let me just give a quick overview of the sort of the schematic of sort of the idea behind these instruments. So there's really these are all related, but the first order process is X-ray absorption spectroscopy. So this is shown here. You have X-rays coming into a liquid film, for instance, and measure the diode. So you measure the absorption through the sample. What this allows us to do is promote a core electron, for instance, into this unoccupied band. And by changing the incoming energy, one can map out this band spectra. So this is a first order process, allows us to map out the unoccupied states. In a similar way, the second order process, which is qRIXS, is once there's a hole created in a core shell, for instance, there's a whole a number of states here in this occupied band, which can decay down and fill this hole. And by doing that, I forgot to mention the X-rays coming in is what promotes for the absorption. The X-ray coming in promotes the electron unoccupied band. When this decay channel occurs, an X-ray is emitted. And by studying the energy spectrum of these emitted X-rays, one's able to map out this occupied band. So this is sort of the main idea. How is this done? You can see X-rays coming in, X-rays get emitted. We typically use these grading spectrometers in the soft X-ray range. And what this does is allows the radiation to be dispersed along, along the spectrum shown here by this rainbow and detected. So by detecting the spectrum, one is able to see the different excitations occurring in the system. And then of course, adding a pump to see how this changes in time. Here's an example shown to the right of an absorption spectrum. So the first part is the qRIXS portable spectrometer. So this is a smaller and medium resolving power of about 2000. This was developed by a bunch of smart people, all listed here, mainly by the team at the Lawrence Berkeley Lab, as well as a lot of people at SLAC. And here just sort of schematic again. The idea is just with a spherical mirror, this beam can be focused onto the grating, which disperses it, which we measure the detector, which allows us to look at different parts of the spectrum in chemical, mainly in chemical types of systems. For the qRIXS spectrometer, this is a much larger system, which we'll go see in a minute. And again, I'm not going to go through the details because it's a recording, so you can pause this. But the main focus here is that this will get up to high resolution. So here's showing the spectrometer with the detector. And this, once we get the high resolution gradient, we'll get up to a resolving power of 50,000. So at the cutting edge in terms of energy resolution for these types of systems. And then lastly, in the qRIXS station, there's spectrometers part of it. The other part of it, which is really important, is the sample chamber. This is the sample environment. So this shows where the samples get inserted. And for the qRIXS, I didn't really mention this, but this is mainly looking at excitations in solids. So typically there's a sample which is mounted to a cryostat, so you can control the temperature. It's inserted right here where you see the interaction point. And then there's a number of different kinds of laser systems that can be coupled into the chamber in order to do the kind of study you want. So 800 nanometers, mid-IR, terahertz are a few of the different options, depending on the type of physics one wants to study. And then lastly, I just want to say, we're talking about these energy spectrum, but there's also another development in parallel going on, which is going to be set at this instrument as well, which is related to X-ray photon correlation spectroscopy. This is physically really the same idea, but it's really a different method. And what happens here is, here's a picture of an additional development we're doing, where a detector is placed a certain distance from the sample and simply measures the X-ray scatter, the coherent X-ray scattering from the system. If we take advantage of the coherence of the X-ray beam and have very short pulses closely spaced together, we can, instead of pumping the system and look at the excitations and how they decay, we can instead compare them to each other and look at how the system is fluctuating in equilibrium. By doing this, we can study very low energy fluctuations in the system. So here's a paper based on some work by Seberg, who's done this recently, and this is a development we're in the process of doing right now. So it's just a sort of a side note of a parallel effort that's going on to study these fluctuations in these kinds of materials and really understand the low energy excitations in quantum materials. So maybe this is the most important part of the talk if you're thinking about doing an experiment, which is the timeline. So Run 21 is going to start in about 2 months. And the first part of this is going to be commissioning these new instruments. First commissioning the new Accelerator, which is ramping up to this high repetition rate, which I'm sure everyone's been talking about and you've heard about. So this is the first part is a commissioning of the Accelerator. And then there's going to be a number of commissioning activities for these different soft X-ray instruments that are part of LCLS2. Soon after, we're going to start early science commissioning. So this is a good chance for you in the audience. If you're thinking about different types of measurements to make on these LCLS2 instruments, this is the time to think about that. And we're beginning to think about there's a lot of scientific cases for these new instruments and how we're going to use them. But really the question is right now, what's the first early science experiments to do and sort of being a part of that and getting the new ideas. So as you can see, there's TMO and qRIXS studies first, and then the qRIXS will be coming soon. So the qRIXS is being constructed right now, but they'll have to go on commissioning, and then there'll be the latter part of this time frame to do early science there. So just like to summarize here, again, want to just point out Georgi Dikovsky is really the person behind all this development of these instruments, as well as this team here, a very strong team which has put this together. Again, I'm just talking about this. I haven't done any of the work. This is really the team here. And here's just a summary of sort of what we've been talking about. Lastly, I just want to point out we have an open qRIXS scientist position. So if any of this is interesting to you or throughout the course of these workshops, this is striking up some interest or intrigue, please reach out to Georgi about this position. So it's a position we're hoping to fill soon. So with that, I'd like to thank you for your attention. There will be a time for questions later, but right now I want to show you over to the instruments and show you live these instruments and just point some things out. So with that, I'd like to thank you for your attention, and let's go to the next part of the talk. Thanks.
All right, welcome to Experimental Hutch 2.2. This is the resonant inelastic X-ray scattering instrument that I'm going to tell you about. First, we go in here where the control room is. This here is where all the measurements are made. To control the experiments, collect the data, do the scientific experiments, all happens here. Of all the work going in the hutch. So let's go take a look at that. This is the qRIXS hutch. This is one of the new instruments for LCLS2, so high repetition rate. We're going to come in and take a look. As you come in here, the X-rays are going from the right to the left, so this is the beam line. And let me show you a little closer up about the instrument. This is a new instrument that was designed for LCLS2, so the beam actually starts on the floor below us. It comes up through the ceiling, out of the wall here. Can we take a quick look here? So the beam comes from the floor below up here into a mirror which deflects the beam horizontally to do the experiments. This is where all the experiments happen for this system. Right here we have two mirror components. So these are important for this system because they're KV optical mirrors. So we have the horizontal and vertical mirrors, which are grazing incidents. The beam reflects off the mirror, and the curved mirror allows us to focus the beam. I should say too, these are all soft X-rays. So all the X-rays going into this instrument are from about 250 eV to 2000 electron volts. So because of the soft X-rays, they have to, everything's got to be under ultra high vacuum. So these two mirrors focus the beam into the center of, this is the main qRIXS station where the sample gets held. So right now it's still being constructed, so it's not here right now, but the beam gets focused to the center of this tank from about a couple of microns up to, say, a millimeter. The solid sample gets inserted from the top. And again, it's not here right now, but it's across that, which puts the sample in the beam. This right here is the main qRIXS spectrometer you see here. So this is the component I discussed earlier about the spectroscopy, which gives you the spectrum of the beam. So what happens is radiation gets emitted from the sample into this mirror system. Here there's a spherical mirror. So it's a spherical mirror, which again focuses the beam down to the detector here. The purpose of this is to select the different energies being scattered from the sample and to select which energies are most important for the physics we're trying to study. And now comes to the reason, why do we call it the qRIXS instrument? This is the most important question. And it's because qRIXS is the resonant inelastic X-ray scattering. The qRIXS is the momentum resolution. So if you look at the structure here, the whole apparatus moves along this arc. It goes from about 135 degrees and it swings down till about, I think it's about 35 degrees or so. So you take a close look at this. So here's the spectrometer, here's the detector. The detector housed at the end is what gives you the spectrum at the end, so you can see the different things being scattered from the sample. So based on, I know everyone here is thinking about types of experiments, so based on the kind of experiment you want to do, specifically in solids, you try to calculate what momentum resolution you're interested in, what energies, and you set up the experiment based on to see what kind of thing you want to study. There's an additional component here which I also discussed briefly, which is another version of the qRIXS, which is the time-dependent version. So for that, we're developing another end station, which is not, it hasn't been constructed yet, but it'll be a tank that goes right here and has a detector which directly measures the beam coming from this chamber. So right now it looks like a tank, you can't see it, but there's a rotary seal. So there's a flange over there, you probably can't see it over here. And that flange rotates along this slot. So we'll have the opening coming right here with a connection to keep it in ultra high vacuum. And we'll have a detector sitting here to measure directly the scattered radiation. This will allow us to make the time correlations and really measure very low energy fluctuations in the system. So that's the qRIXS instrument. Briefly about that. Any questions, anybody? And then there's another component here, which I'll say briefly, which is called qRIXS. So the idea here is the same thing. You have the same beam line. The beam comes in here, but now the beam gets focused in the center here. And here we have a liquid jet. So that's a thin stream of liquid traveling vertically through the system. The X-rays interact with it. And again, we do resonant inelastic X-ray scattering, but now it's from liquids. Now the momentum resolution is not so important. And right here we have a spectrometer. This is a miniature version of the big one, where we have a miniature spectrometer, which is medium resolution, which allows us to see the spectrum from different kinds of chemical reactions and molecules. So this is the qRIXS sensation. And then lastly, qRIXS, qRIXS, we have a blank space here at the end. And this is for upcoming future experiments, which you'll see other workshops about in the users meeting. So there's two different end stations that are coming, which we'll tell you more about later. Thanks a lot.